At 2 then. Okay, so Richardson is similar to the Romberg, and the idea is that we have this integral approximation that's OHP. That is the true integral minus my approximation is about equal to some constant over n to the p. So we're saying this is OHP. And so the idea is we can weight these averages in such a way. So like if it's trapezoid, p is equal to 2. If it's Simpson, p is 4, right? Because we talked about OH squared and OH to the fourth. So if we have the error or have the step size in trapezoidal rule, our error should go down by about a fourth. If we have the error in Simpson's rule, our error should go down by a 16th, ratio of 16. So we could use that to our advantage and say, well, our integral then is going to be an approximation of 2 to the p minus 1 to the p I2n minus in. So we double the number of subintervals, put greater weight on that, subtract off of our approximation with n, and that should give us a better approximation for I. So we started with this one last time where we knew the results. And we calculated, like at each subinterval, 0, put in 1, you get 3, put in 2, you get 2 squared times 3 is 12, and all the way down. And if you do this trapezoidal rule with 2 subintervals, you get 576. And if you do it with trapezoidal with 4 subintervals, that the length of h is 2, so h over 2, 1, 2, 2, 1, or 1, 2, 2, 2, 1, you get 528. In one subinterval, you get 1/2 h over 2, 1, 2, 2, 2, 2, 2, 2, 2, 2, 2, 1, and you get 516. So that's not the true answer yet. However, we can use this sort of approximation to our advantage. That's a repeat of that similar slide. So we're going to use Richardson. In our example, we're using a trapezoidal rule with p equals 2. And we're using our order of n equals 2. So R4, that stands for Romberg, will be over 1 to the 2 squared minus 1, 2 to the squared I4 minus I2. So we're going to take a weighted average of our previous terms. So this would be 1/3, 4 times I4 minus I2. So let's see what we got in our previous slide, what it was for 4. 528. Minus 576. And divide that by 3. And we get 512. Which is the correct answer. So what we're doing is we're using our error analysis that at some constant, well, in other words, it's OHP, to our advantage, to sort of take a weighted average to sort of speed up our solution. Okay, so this is a a standard trick. I don't know if trick is the right word, but yeah.
So the IN is arrived at by
whatever method we have, whatever trapezoidal, Simpsons. You can use the left-hand rule if you wanted to. Yeah.
So the book uses 4
Yes.
as a coefficient. Is that a better approximation?
I don't know why the book uses 4. Every other book I've seen uses 2.
So is there a difference at all, or is it just choice?
No. So the book uses powers of 4 instead. K equals 1 for trapezoidal rule and K equals 2 for Simpsons rule. So you kind of have to make the adjustment. I really haven't seen the 4 business used that much.
Okay.
But, shouldn't make any discouraging remarks about engineers. No, it's more the fact that sometimes you're just on different wavelengths. When you kind of have a discipline that grows up in its own discipline and kind of gets its own answers in other disciplines. So they're kind of the same, but they use different notation. So yeah, you should watch out for this, for powers of 4 instead, because, this could be 4 to the first. Generally, p is even. So let's see if I can translate this. This would be 4 to the p over 2, 2 to the p over 2, I2n minus in. I think that's what they use, right? They use like...
It had 4 on the top, and it was...
4 to the p, so 4 to the k.
Yeah, and it was k minus 1.
Oh, I keep forgetting the 1 there.
But it was k minus 1 in the exponent, too.
Really?
Yeah.
So 4 to the k minus 1 in the exponent here?
Yeah.
Oh, okay. So yeah, you have to kind of make translation, going from English to German. All right, let's kind of see why that works. Putting those two things together. One is that if you have I minus maybe double the subintervals, this is about equal to C over 2n to the p. And that's equal to C to the p over np. This is sort of how we pick out our weighted average. So what I can do is take these two sides and simplify this. Okay, so I'm going to multiply the 2p to this side. So I get 2p I minus I to the 2n is about equal to C over np. But C over np is approximately what? I minus in. Now let's go ahead and solve for I. So we get everything on this side with an I on it, and everything on this side with everything else. And you can see then that I is about equal to 1 over 2p minus 1 to the p I to the 2n minus in. So that OH squared stuff and OH cubed stuff kind of comes in handy as far as speeding up the approximation that you have. So you can look at some of the charts they have. So here you have 0.172, 0.68, and then you have the same thing, you just have one more estimate. Then you have 4 estimates. So you take a weighted average of this one, you get 1.3647. Take a weighted average of this one, Well, and then you can take another weighted average to get 1.6403. Take a weighted average of this one, take a weighted average of this one, take a weighted average of this one, and you get more of an approximation. So this is sort of like your OH8 that you were asking about then. So really, what you need is 4 estimates, maybe with 2 subintervals, 4 subintervals, 6 subintervals, and 8 subintervals. And then weight each of these averages up, and then that gives you maybe a pretty good approximation then.
And so the way that we're weighting them is going to be with that?
Yeah, either this 1 over 2p minus 1 to the p, or 1 over 4k minus 1 minus 1. They're the same, it's just you have to make sure you get the right k's and the right p's.
Okay.
So do the step sizes, or the number of intervals have to double for each estimate?
Yeah.
Okay.
Yeah.
So 2, 4, 6, 8 would not work.
Oh, I see what you're saying. You're right, 2, 4, 8, 16.
Okay.
Yeah. However, you don't have to restrict this just to trapezoidal or Simpsons rule. There are sometimes you can use this with quadrature as well. If the quadrature has the right error estimate, you can also speed up the quadrature. So
Okay, so you could just go like 2 points, 3 points, 4 points.
yeah, but you kind of have to check this out again. So yeah, this is the book's version. 1 over 4 minus 1, 4 minus I2, which is, basically what this is. Now we can extend this, and this is what the book does. And j plus 1, k minus 1, j to the k minus 1. And let's just kind of see how that works. So the k minus 1 and k minus 1 is just the order of the method that you use. The j plus 1 and the j is just how many over you go in the columns. Like how many times did you weight this average. So there is this something called this Romberg integration algorithm, and it generalizes Richardson. So we're going to use a weighted average on the weighted average to get an improved integral estimate. And always you put the weight on the better integral estimate. Weighted averages are big in numerical analysis ideas. All right, this doesn't relate to this class per se, but this is Pascal's triangle. So to get like P22, zero, 1, 2, 3. Like P33 would be P22 plus P23. You add those together, get 1. P32 would be P12 plus P22, and that would give you P23. And it's sort of the combination, the addition formula for the Pascal's triangle. So let's see what it would be for Richardson then. Okay, so here's what happens. You start off with just a integral with one trapezoid. And keep using equally spaced intervals. And then R 1, 0 will be a trapezoid with two trapezoidal world with two trapezoids. 3 trapezoids all the way down to n plus 1 trapezoids. So you have, 2 to the n subintervals here. 2 to the 0, 1 subinterval, 2 to the first, 2 subintervals, 2 to the second, 4 subintervals, 8, 16, and all the way down. To find this, then, you're going to use the weighted average to get R11. So you have this recursive formula where it's like 1/3 of 4 times this minus this. 1/3, 4 times this minus this. 1/3, 4 times this times this. And so you can then go across in each time. And so you get a recursive formula and since you're having the h, you get 1/2 R00 plus h times the average of a plus b over 2. So you have your old one, and then you add in the halfway points. Let me show you one more slide, and maybe that will be a little easier to say. You don't want to you want to reuse. You want to reuse what you have. So here's one subinterval. So you have this value and this value. You add in another subinterval. Well, you already have these values already, so you just need to take into account this one. And now, since you have these 3 subintervals, you just have to take these one in here, sort of the halfway points or the midpoints of these. And then you want to add those in. So there's kind of this way of getting your trapezoidal rule just a little bit simpler. You don't want to start all over. You want to reuse. Reuse, reduce, recycle. Has other applications to this. So you really love having equal subintervals. I know that equal subintervals are not always the best, but for at least calculation purposes, reusing it really helps out with equal subintervals. And then this is how we would generate our array. Once you get this, where you add in the subintervals, then you can use this recursive formula and keep going until you find what your estimate is. And you go from OH squared to OH to the 4th to OH to the 6th to OH to the 8th and so forth, OH to the 10th. So it really is kind of an interesting way of calculating that. So does that make sense in terms of, first of all, creating your trapezoids by adding in midway points? There's some details there. You can look them up. But then the next column, you can use this recursive formula to find this out. So basically, what your previous one is, you could take this weighted average, which turns out to be just our general formula, what we have over there. So let's try this. If we have R42 is 8 and R32 is 1, go ahead and find out what the next, what value you can find out for. Yep. You can find R4, 3. Because in this case, n is 4 and m is 3. And you could use the formula on the bottom, 1 over 4 to the third minus 1, 4 to the third, R 4, 2 minus R 3, 2. Did I plug those in right? So it's kind of like Pascal's triangle where you add these. The next one you just have different weights. And then you could solve this. Is that 4 to the third is 64? So 1 over 63, 64 times 8 minus 1. And that would give us what our next iteration would be. Well, the question is why 4? It goes back again to what series? Taylor series, yes. See, we have 4 people with Taylor. 5. 5 of the 8 of you have Taylor sweatshirts on. It's a good sign for our school. Basically, it's where you knock off the in-between parts and you get the 4s down at this part. We'll skip over that derivation, but that's where the derivation comes from. It just goes back to Taylor series and knocking off some previous values. But it does happen that our error then becomes h to the 4th, OH4. And so when you knock off these terms using Taylor series, you get that step up each time. Yeah, and then we could do some algebra and stuff. There is some further research you can do if that's finding the nice recursion formulas using what are called Bernoulli numbers. And again, this is another example of using the Taylor series to get more accurate formulas. Taylor series by itself is not very accurate, but it's a very fruitful formula. Because if it's fruitful, it then it does what?
It's helpful.
And leading to what? Yeah, further research, yeah. So it's kind of the foundation, but by itself it's not so great. But in practice, it gets us a lot of these great formulas and whatever. It's kind of where we start off with. Doing some combinations allow us to get rid of the terms. Now, if you take this column, then this limit as n goes to infinity will be the integral from a to b of fx dx, as long as f is Riemann integrable. Have you talked about Riemann integral yet?
Oh, yeah.
Did you talk about advanced calculus, what Riemann integral was?
Yeah.
Okay. I don't know if you will talk about Riemann integral. Function being Riemann integral. Depends on which real analysis emphasis. Real analysis is so broad and broad that you could have 4 different classes with only like 10% each the same. Okay, differentiation. This is kind of where the roles are flipped. Which one, if you're given a function, you can always differentiate, right? It may take you forever, but you can always differentiate and get a solution. You can't always integrate. You don't have the right u substitution, the integration by parts. They don't always have a symbolic answer. However, the roles are reversed here. in that, in general, differentiation is more sensitive than integration. Integration, in some sense, is more well-conditioned. Differentiation, though, is not. It's usually very sensitive. I think probably I was the most sensitive maybe in 7th grade. Trying to think. When do you think you were the most sensitive, Jessica? No idea? Are you one that has blocked entirely your junior high experience?
My middle school experience wasn't that bad.
Do you think you're more sensitive now than when you were in 7th grade?
I have no idea.
Okay. Maybe you can ask your mother
Okay.
to kind of see what it was. My mom said my dad was very obnoxious when he was in college, so she said I'm less obnoxious than my dad. I don't know if that's good or bad, but so maybe you could kind of think of as differentiation as like when you're younger you're more sensitive, and then when you're older you're not. Do you cry after every time you lose?
No.
Yeah. See, I cried when in 7th grade anytime I lost. I was like so upset. Yeah, I think that's part of. You were more mature than I was, so at that time. All right, we can use the same sort of thing for derivatives and the Rhomberg differentiation. So more robust is integration in general. And let's try the same thing. Let's try to calculate the derivative at 0.5 minutes. So the concentration of a drug in the bloodstream, sort of like your problem of trying to figure out when to give the dosage. The derivative at 0.5 minutes, and then what are the units of the derivative? How would you estimate the derivative at 0.5?
Probably using like the point before and it.
Okay, so kind of do the change in y, 0 over negative 0.1?
Yeah.
Okay, would anybody else do anything different?
You could fit a quadratic between the 3 points.
Okay, very good. You could fit a quadratic there between the two. There's also this formula that you could take each side. You could take 1.0 minus 0.97 over 0.4 over 0.6 minus 0.6, all of those. Well, just like integration, you have the same sort of deal with differentiation. Oh, and the second derivative either. So here are your possibilities. This is sort of Alex's idea. Take 1 point away. Here's another way. You could do a left-sided one. Take 2 points to the left, 1 point to the left, and then you just need to weight it, -1, 4, and 3, and divide by 2h. And then the second derivative, you could also do it that way, and just take left sides. These formulas are in your book, by the way. You could also use centered formulas, and these are, notice that these are like OH squared, OH to the fourth, and something. So this is the one where you take a point to the right, take a point to the left, and then subtract its 2h. But you could also do another weighted average of -1, 8, -8, 1, 12h. And this is OH to the fourth. You can also do a second derivative, OH squared, and then even a longer one for OH to the fourth. Where would these formulas come from? Yeah, the Taylor series. You can all find that from the Taylor series. If you look in your book, I believe it's not that one, but I believe it's here on page 655. Here are the finite divided differences. And you can get third derivatives, fourth derivatives, all these ideas of calculating the various derivatives. Yeah, here's the -1, 8, -8, 1, and the second derivative. You can find the third derivative, the jerk.
Isn't that the fourth derivative?
And what?
Is that the fourth?
I thought the jerk was the third derivative. I
Yeah,
forget what the
it-
fourth derivative is.
You're right.
There's a word for the
Snap.
fourth. Is that the snap?
I think so.
Snap. Okay. Is snap a bad word? No? Okay. Just curious. You say it is, or you just...
Snap, no.
All right. So I can say, oh, snap, when I make a mistake, and that would still be acceptable. Okay, so to improve the estimate, we can either do two things. One is decrease the
Step
step size, or use the higher formula that uses
better points.
more points.
More points.
Yeah, or better points, more points. Or we can break out the I guess I'll erase this right here.
Something with Romberg.
Yeah, Richardson. Break out the Richardson. So decrease the step size. Use the higher order formula. Remember a forward difference is OH. If you use a center difference, it's OH squared. If you use a larger difference, I think it was OH to the third, maybe OH to the fourth. Or break out the Richardson. And we can do the same sort of deal here. Do a weighted average on cutting it in half and to calculate what our new one would be. So we could do the same thing from Richardson extrapolation. It's the same thing, only we use the letter D for derivative instead of I for integration. Do a weighted average, and if we do a centered valid, we get OH to the fourth. In this case, your two end, they don't reuse the same points. You're like getting halfway closer and halfway closer and halfway closer. And that gives you OH to the fourth.
Is that dm minus dn?
No, d to the 2n minus dn. So and we may come back to that if we go to the lab. So those are all assuming that we have equally spaced points, and they're useful for trying to estimate the derivative of function. And it only works if we have equally spaced points. What if we have unequally spaced points? What do we do? Any ideas?
You try to do an approximation and use that with equal space.
So back to maybe quadratic or maybe a spline. Any other ideas? Yeah, I think those are Yeah, fit a second order Lagrange interpolating polynomials and differentiate. You can find that on page 58. And this is advantages can be used to estimate the derivative at any point within the range of the 3 points, not just the points that you're looking at, but any other points in between. And they don't have to be equally spaced. And it's of the same accuracy as center difference. So that's pretty good. The downside is that you can't, anyway, so you can do the interpolating polynomial and do the approximation. And if you actually have equally spaced points, these are just h squared and 2h, and so you just get the same center difference formula. But if they're unequally spaced, you can use those. So there are formulas you can use for that. Now, with data, we often have measurement errors, and that's why we have the smoothing business, the least squares regression business. And the process of differentiation amplifies these errors. So let's suppose I was trying to approximate this error, this derivative right here, and that's a pretty good derivative, a slope of that part. But if I made a measurement error, like this part, then my slope is much, much worse. Particularly in the y variation, or the x variation, well, I guess it'd be the y variation, you're especially if you have very small numbers and you're dividing by very small numbers or big numbers like that, you're really going to change what the slope is. So it's very sensitive to errors, and measurement errors in particular. With area, small area, you just cut off a little piece of the pie. It's still the same kind of piece of the pie. You haven't lost very much. But with differentiation, it's a little different and is really sensitive in this part. I think it'll be about time for you to have the problem on how did Doug Henning, was that his name? Made the Statue of Liberty disappear. Okay, don't look up the answer, but I think that will be this next coming weeks then. Differentiation tends to be unstable. It amplifies error. Integration tends to be forgiving. The errors kind of balance off. Integration and differentiate power series is also something you could do. That's all I'm rambling about that. There are other improved methods for this. One is beyond this course. You do the adaptive Simpsons integration rule. You divide the area into each equal lengths, and you figure out each error within each subinterval, and then you adjust. And it's really nice for complicated functions, high variations at certain points, but we're not going to use that. The other thing you do is fit cubic splines and integrate those. And then you can use a variety of quadrature approaches and adaptive quadrature approaches. One of the reasons why I wanted us to go through the quadrature approaches, if you use the help and ask Mathematica how they do their integration, invariably they'll say we used an adaptive quadrature approach. In short, there is much, much more to the story. But you didn't realize that there's much, it's active area of active research as to how to get better integration formulas, how to do better. Particularly now that we have more powerful computers, there are possibilities that we can cut down the propagation error by increasing the number devoted to storage. And then there's some new ways that we can look at. As a matter of fact, one way is you just do a Monte Carlo method. You just take your integral and you just take random points and you count whether they're underneath the curve or above the curve, and the percentage of points will give you a percentage of the area, and then that gives you your integral. So you can use your simulation to find out what your integral is. Okay, so now we move on to differential equations, which is the model, the language of change. And we're going to focus mostly on the error. We have a whole course in differential equations. We are going to focus on the error that comes about with this. But we need to start off with some notation. So an ordinary differential equation, we're going to write it as the form of y prime is equal to a function of x and y. Okay, so we are saying that y is a function of x, but here we're saying the derivative is a function of x and y. So the solutions to differential equations are functions. And let's just kind of go through some examples. I wish I could load this up a bit. And what we're going to do is we're going to do our numerical techniques on this multivariate function. So if we had y prime is equal to y plus 1, gives us that f of x z would be z plus 1, right? So this is my second variable, and z plus 1. Y prime equal to 6t minus 1 would be f of t z 6t minus 1. And y prime equal to 3y minus 5x plus 1 would give me
3 minus 5x.
Yeah. So our derivative function is the thing that we're going to look at. So at each point of xz or xy, this part right here represents the slope at that particular point. And what we do then is we look at slope fields. We already looked at slope fields when you're looking at your owls and hawks. We're only going to focus on numerical methods here. So here, my y prime is equal to x plus y, or x plus z. And every point that we go on here, like say we're here at 0, 0, we would have a slope of 0, so we would graph a little, like a line there for a slope of 0. If we were at the point 1, 1, we'd have a slope of 2. So we put a slope of 2 there. And at any given point. And the thing we can then do is we can, pick a point and just follow along in our canoe to see what our solution might be. Would you say this one is well-conditioned or ill-conditioned? ill condition because it's very sensitive to points. Now, if we're over here, everybody's going to end up at the same spot. But the equilibrium points, where it's not changing in some sense, is ill-conditioned. One of the ways we do this is say, hey, we're at this point, we know what our slope is. Our next point should be whatever our h is times our slope plus our y1 will be our new point. This in some sense is what's called Euler's method to kind of get an approximation for the next value. Did Dr. Thompson do any Euler's method in Cup 2? Any differential equations whatsoever? Oh, I'll have to talk to him. So using that kind of formula then is we let our new point x of t plus h this is our is going to be our old point plus how far we want to go times the slope at our current point. So again, this is the slope. This in some sense is our multiplier, and this is our old point. And this is our new point. And from this we can approximate how our function will do. We just kind of keep going along these curves. Okay. All right. So we talked about quadrature and we talked about Romberg, both for integration and differentiation, for using our error methods to actually get us better methods just by doing a weighted average. They're going to have the same sort of deal here when we talk about differential equations. The main point of differential equations for us is to identify and control the error. And really that's our focus for this part right here. Okay. Have a good Wednesday. Can't believe it's so late in the year and we're going to get a 58-degree day. I remember in 1991, it snowed 24 inches in Minneapolis this weekend. It's a great Halloween snowstorm.
Did you say Minneapolis or Indiana?
Minneapolis, M-I-N-N, yeah.
I feel like it's much worse.
Yeah, they had, last week I think they had 12 inches.
That was like...
It just kept snowing.